that we've talked about strong electrolytes, it's time to start talking about weak electrolytes. Now, your main difference is that strong electrolytes, because they do dissociate to 100%, most of the math that's involved with them is all going to be stoichiometry based, and then very simple pH calculations at the end of them. Whereas with weak electrolytes, because weak electrolytes do not dissociate to 100%, what is done can kind of be undone. So we do see this balancing act between reactant and product. Those are all subject to equilibrium and therefore are all going to be equilibrium problems. So it's going to be a little bit more complicated to try and find our final concentrations of materials, but after that it's the same deal. It's just going to be pH calculations. So let's start to take a little bit of a closer look at weak electrolytes. So again, weak electrolyte is anything that basically does not dissociate to 100%. So at this point, we're going to narrow our definition down a little bit to any salt, which we would normally kind of label as solid, not aqueous. Although we're taught in first year chemistry that anything labeled with S is completely insoluble, implying that it does not dissociate at all, in fact, particles of both of those ions do dissociate into solution. That's actually going to drive our next study in equilibrium. For this chapter, we're really going to focus in mostly on the acids and the bases. Now, weak acids, again, do not dissociate to 100%. They are going to have K values that go along with them. To try and be a little specific, they're going to be Kas. Weak bases that do not dissociate to 100% are also going to have K values, and those are called Kbs. So let's take a look and try and figure out what is a weak acid and what is a weak base. Well, according to Arrhenius theory, which is essentially what you're taught during first year chemistry, is that an acid is anything that can donate hydrogen to your solution, anything that can donate H+. So things that seem very familiar to us, like HCl, HBr, your strong acids, all of those are considered to be Arrhenius. In other words, actually anything that starts with hydrogen. However, it was very limited, and we did find that there were some chemicals that once you started putting them into water did actually have some acidic properties. So the team of Bronsted and Lowry actually expanded upon this theory and said that an acid is now considered to be a proton donor. Anything that when you put it into a solution seems to want to donate H1+ to the system is going to be an acid. So for our purposes, a weak acid can now be defined as anything that starts with H, anything that starts with that hydrogen, or anything that includes the organic functional group COOH, or a carboxylic acid group. I want to take a little bit more of a closer look at what a carboxylic acid is and how it actually qualifies as an acid. So here you have basically the condensed chemical formula RCOOH, or Cu, plus H2O. I made you a structural drawing underneath there, where the yellow atom is carbon, all of the blue atoms are oxygen, and the orange atoms are hydrogen. So you'll see that your carboxylic acid, your Cu, is connected to essentially anything. It could be literally anything, usually a long carbon chain. And your water molecule is about to come over and kind of play around with your Cu of this lovely molecule. So things to remember is that water, because of its molecular structure, does have one end that tends to be a little electropositive or partially positive, and the oxygen side of it does tend to be electronegative. It is very attracted to other electropositive type compounds. On the carboxylic acid side, the oxygen that's connected to the hydrogen is very electronegative, and therefore will actually give the molecule a partially negative charge in that zone, creating an area that is partially electropositive for that hydrogen. So there's a natural attraction between the oxygen of the water and the hydrogen from a carboxylic acid. In fact, it's so strong that it actually does form a hydrogen bond. And what we know about hydrogen bonds is that occasionally you can actually convince the hydrogen of the original molecule to let it go and to donate it to water. So we can actually get that hydrogen to pop off, forming a hydronium ion and leaving its previous bond behind in the form of an electron pair. Now this is why carboxylic acid can actually act as an acid. Even though we see OH in the formula, it does not indicate that it's a base. Now why can this happen? Why can we leave an electron pair on this oxygen? It doesn't seem to make sense. So again, we have a +1 charge now on the water molecule that has become hydronium, and what got left behind on that carboxylic acid is a -1 charge. Now, nature really does not like charge separation, so there must be some form of stability in this structure, and in fact there is. Let's look at the carboxylate anion. That's what's left over after the hydrogen falls away from the carboxylic acid. What we'll notice is that an electron pair decides to kind of donate itself as a bond between the oxygen and the carbon center. Now, when that happens, that carbon will essentially have 5 bonds. We know that carbon doesn't like that, so it has to let go of another bond, but it has a choice as to what bond it would like to let go. So it convinces the second oxygen to give up one of those bonds and take that lone pair onto itself, essentially shifting the -1 charge onto the next oxygen. Isn't that interesting? So essentially, that second oxygen on the top half now has the same problem that the original oxygen did in the first place. It still has charge separation, but stability here is gained because it doesn't have to have it 100% of the time. You can actually toggle between these two states of being. And what do we call it when we can actually choose where one of the double bonds goes inside of a structure? This is resonance. Resonance creates stability inside of your structures. And it's for this reason that the carboxylate ion is extremely stable in solution and why it can donate a hydrogen and act in an acidic fashion. Time to focus on our weak bases. Now again, the first acid-base theory that came along was defined by Arrhenius, and Arrhenius kept it very simple. He said that it was anything that can donate hydroxide to a solution. So in other words, your sodium hydroxide, lithium hydroxide, essentially almost limiting it to your strong bases. Bronsted and Lowry decided that it was way too limiting because scientists were seeing that as you put other chemicals into solution, they had basic properties. So they expanded it to be anything that can actually act as a proton or H1+ acceptor. So now our definition broadens to not only what Arrhenius said that we can use as a base, but also now things that include nitrogen. A base now no longer necessarily has to end in hydroxide. You should look for hydroxide type compounds and any compound with nitrogen on the inside of it. All of those will act in a basic fashion. So I have a little animation for you on the next screen. I really want you to kind of take a look at it carefully. So we have our NH3 compound here, and you can clearly see that there is a lone pair of electrons on it. We have a water molecule right next door, and what you just saw, which I will play again, is that the water molecule basically sidles up right next to the NH3, and because of that lone pair of electrons becomes very attracted to the hydrogen of the water, forming a new association and therefore a new bond. Now that leaves you with NH4 and hydroxide ion. So in this sense, even though there's no hydroxide in NH3, it can still act as a base because once it goes into water, it creates hydroxide. Now for this reason, you do need to be a little bit careful when you're writing the hydrolysis equation for a weak base that does contain nitrogen in it. Water does need to be a reactant because on the other side, there'd be no source of hydroxide ion. So again, please do make sure that water is part of that equation. So let's take a look and see what these problems are going to look like. How are we going to end up calculating the concentration of hydroxide or hydronium? Well, here is another equation for the dissociation of a weak acid. So very simply, you can see that in order to calculate the equilibrium constant, we would again take the concentration of the products over the concentration of the reactants. Now that would end up being hydronium times the anion divided by the original acid times water. And don't forget, we don't include water as part of this calculation because its activity, being pure liquid, would be 1. Now, luckily for acetic acid, which is CH3CuO, is 1.8 times 10 to the negative fifth. Some things to know about your acid strength as regards to your K value. The smaller the K value, the weaker the acid. The larger the K value, the stronger the acid. When your K values are large, they do push very far to the product side. In other words, dissociating more closely to 100%. Whereas your very, very small K values, well, you're not going to be pushing very far to the product side. You're not going to be making a lot of hydronium. You're not dissociating very fully. Therefore, you can't be as strong. And ionization constants, by the way, these Kas can be experimentally determined in a large number of ways, many of which we will actually explore in class.